Alright, welcome back to video 5.2. Today we're going to continue talking about the wave nature of light, and we're going to talk about how to do some calculations with it. So the first thing to remember is that light is electrons. Okay? So, visible light is electromagnetic radiation. What that means, it's electrons. It's probably aligned upon the magnetic poles of Earth or the Sun, and it is a form of energy that exhibits wave-like behavior as it travels through space. All waves can be described by several characteristics, and we're going to look at those characteristics. So, when we think about a wave and it goes through space, it is going to look a little bit like this right here. It's going to go up. The top of that wave is called the crest. It's going to go down, and then it's going to travel through the origin. The origin is this black line. When it goes down the bottom of the wave, that is called the trough. Okay? Then we go back up through the origin, back up to the top, that is the crest. The distance from one crest to one crest, or one trough to one trough, is called a wavelength. So a wavelength, and there's that lambda, that's the symbol for wavelength. It is the shortest distance between equivalent points on a continuous wave. So I can measure wavelength from crest to crest or trough to trough. I cannot measure it from trough to crest. It has to be from equivalent points on a continuous wave. The amplitude is the wave's height from the origin to the crest. So the origin, remember, is that black line. It runs through the middle. The height from the origin to the crest is called the amplitude. Theoretically, the amplitude should be the same from origin to crest or origin to trough. So, wavelength, amplitude, we know what the crest is, we know what the trough is, we know what the origin is. There's also frequency. So frequency, remember V, nu, is the number of waves that pass a given point per second. So, how many waves, so remember that's crest to crest or trough to trough, how many waves pass per second? So the units are hertz, which are Hz, and that's going to be 1 over s, or s to the negative 1. So, if something has a long wavelength, that means there's a long distance between the crest, or between the trough. It's going to have a lower frequency, because remember, frequency is the number of waves that pass a given point per second. So if something has a long wavelength, that means it's going to be traveling slower. It's not going to be as frequent because it's going to take a longer amount of time for those crests to pass a specific point. If it's going to have a higher frequency, it's going to have a shorter wavelength. So that means that it's a shorter wavelength, crest to crest is not as far apart, so they're going to pass more quickly. Frequency and wavelength are indirectly related. When one goes up, the other goes down. So here's the equation that we're always going to use when we are calculating the wave nature of light. So, when we are using, I don't know what that is, wave nature. Alright, C equals lambda times nu. What that means is the speed of light, C, is equal to the wavelength times the frequency. The speed of light is the product of its wavelength times frequency. Speed of light is a constant, and it will always be 3 times 10 to the 8th meters per second. That is the speed of light that we observe. All of our light comes from the sun, and that is the speed of yellow light. The wavelength, as we've already defined, sorry I'm yawning, the wavelength is the shortest distance between equivalent points on a continuous wave. So, the distance from crest to crest, and the frequency is the number of waves that pass a given point per second. So you always have to remember that wavelength times frequency equals the speed of light, and we know the speed of light because it is 3 times 10 to the 8th meters per second. So right here, microwaves are used to cook food and transmit information. What you have in your kitchen was originally used for shortwave radio transmissions. That's what microwaves are. They are waves traveling through space. So right here it says, what is the wavelength of a microwave that has a frequency of 3.44 times 10 to the 9th hertz? So right here, it's asking me for wavelength, and it gives me frequency. So the first thing I'm going to do is I'm going to write C equals wavelength times frequency. So I know that C is the speed of light, so that's going to be 3 times 10 to the 8th meters per second. It asks me for wavelength, that's my unknown, and then it gives me that frequency is 3.44 times 10 to the 9th hertz. So what am I going to do? I'm just going to solve for my unknown. So I divide both sides by 3.44 times 10 to the 9th hertz. So that is going to end up canceling on the right side. And I'm going to plug this into my calculator, and it's really important that you remember to put parentheses. So I'm going to do 3 times 10 to the 8th in parentheses divided by parentheses 3.44 times 10 to the 9th, close parentheses. And my calculator is being slow. I'm going to end up getting my wavelength right there to be 0.087 meters. So what that means is when a microwave has a frequency of 3.44 times 10 to the 9th hertz, so that means it's going to be moving pretty quickly. Its wavelength is 0.0087 meters. So I could convert that to centimeters. And that's a pretty short wavelength. That's only about 87 centimeters. So, or 8 point. Sorry, that would be 8.7 centimeters. So that would be a really small wavelength. So here's another one, and it says, what is the frequency of light? So this time I'm solving for frequency that has a wavelength of 340 nanometers. So I know I'm going to end up using C equals wavelength times frequency. But this time there's something weird, is that this is given to me in nanometers, and I want my wavelength to be in meters, because the speed of light is 3.00 times 10 to the 8th meters per second. That's in meters, so I need to know what the wavelength is in meters and not nanometers. So what I'm going to end up doing is I'm going to start and I'm going to convert 340 nanometers to meters. So I think back to chapter 2 in the conversions, and there were 10 nannies. So this is going to be 10 to the 9th nanometers for every 1 meter. So I'm going to do 340 divided by 10 raised to the 9th. And right there I'm going to get 3.4 times 10 to the negative 7th meters. And so I'm going to plug that in. That is my wavelength. So I'm going to plug that in, 3.4 times 10 to the negative 7th meters as my wavelength. And now I can solve for frequency. So I divide both sides by 3.4 times 10 to the negative 7th meters. On the right side, that ends up canceling. And I'm going to end up getting 8.82 times 10 to the 14th hertz. Because this is frequency, I'm going to make sure that my units are the frequency units, and those are hertz. So, questions? Alright. So the thing to remember is that sunlight contains a continuous range of wavelengths and frequencies, and we can use a prism to separate sunlight into a continuous spectrum of colors. This is because our eyes can only see a little bitty bit of the electromagnetic spectrum, and it includes all forms of electromagnetic radiation. So if you look at this right here, wavelength and frequency, remember that they are indirectly related. When one goes up, the other goes down. Radio waves have a really long wavelength, so they have a really low frequency. This is why radio waves, with their long wavelengths, can travel a really long distance. The Grand Ole Opry is on AM radio, and if you have ever noticed, if you have on your car, if it's AM radio, what that means is 680. That's the frequency it broadcasts on. FM radio is things like 107.5. That means that that's 107.5. That point takes the place of a comma. What that means is FM radio is going to be at a much higher frequency than AM radio. So radio has the longest wavelengths. Microwave have the next longest wavelengths. Microwaves are shorter than radio waves, so they're the next longest. Infrared gets smaller. Then you've got your visible light. Then you have UV rays. And then you have X-rays. Then you have gamma rays. If you notice, the wavelength gets smaller because the wavelength increases as you go from right to left. It gets smaller as you go from left to right. So radio waves are much longer than gamma rays. But as you have those long radio waves, you have small frequencies. As you have short wavelengths in the gamma rays, you're going to have really high frequencies. So that is the wave nature of light.